All right, we're back and we're going to be talking about Newton's second law of motion today, which focuses on the relationship between, force, the mass, and then, of course, the acceleration of the object. If we summed up Newton's second law in a nutshell here, it would be the overall net force is equal to the mass times the acceleration. If you look at the net force here, it's measured in newtons. And don't forget that newtons is really the derived unit for a couple things put together. Do we remember? It's kilograms, meters per second squared. The mass now is measured in kilograms, and then the acceleration is measured in meters per second squared. That should be up here, by the way. But what is overall net force? Well, we're going to explain it a little better, but basically, after all forces cancel out, whatever's left over is your overall net force. We explain that maybe a little bit differently in Newton's first law. We called that the unbalanced force, or the outside force. So maybe keep that in mind. But if you pay attention to this bottom right corner here, you'll see a picture of a gentleman golfing, and he's going to take a swing at a golf ball and a swing at the truck as well. So he's going to hit both the golf ball and the truck with the same force. Now we know that the mass of a golf ball compared to a truck is very small. So that's why we have this little tiny m for the golf ball and this big M for the truck. But if they're both hit with the same force, it makes sense, right, that the little golf ball would accelerate far more than the large truck would with the same amount of force from the golf club. So that idea, that relationship between mass and acceleration, kind of overlaps with Newton's first law. The idea is, if it's a really big mass, it has large inertia, so it's harder to get it to change its state of motion, which means that a net force acting on it won't accelerate it as much as a net force acting on something that has very little mass, which would create a much larger acceleration. If we look into force a little bit more, as you know already, we measure that in newtons, but a net force is really just a combination of all the forces acting on it. And the forces can cancel out. For example, in this picture down here, this young lady is riding her bicycle. She has a forward force of 15 newtons, so that's positive in my eyes, and a backwards frictional force of 20 newtons, which is negative in my eyes. If you add those both up, what's the overall force left over? Well, the overall force is negative 5 newtons, or 5 newtons backwards. So that becomes your net force, which we could designate it as F net. Now, the important thing to realize about net force, and sorry, the picture is cutting it off a little bit, is that according to Newton's second law, net forces are the cause for acceleration. So if you have an overall net force, there must be an acceleration. Net force and acceleration is always in the same direction. So for that bicycle, remember, it was 15 newtons forward, and force of friction was 20 newtons backwards. Since the overall net force then ended up being a negative 5 newtons, since it was in the backwards direction, right, acceleration would also be in that direction. So if you recall from the picture before, if the person was riding their bike forward, but F net is backwards, and so is acceleration, I think it's safe to say that that bicycle is slowing down because velocity and acceleration are going in the opposite direction. If you take a look at net forces up here at these pictures, right, overall, there's 5 and 3. The overall net force ends up being 2 newtons forward. For this one, 3 and 4, the overall net force equals 1 newton forward. If we practice a little bit here, net forces, negative 2 newtons and 8 newtons ends up giving you a positive 6 newtons forward. Positive 10 and positive 2 newtons added up gives you a total of 12 newtons. A negative 8 newtons and a positive 8 newtons ends up giving you no net force. There's another term for that we'll talk about in the next slide, but that is called equilibrium, where your net force is 0 because the forces cancel out. You take a negative 10 newtons here and a positive 8 newtons, you still have an overall 2 newtons left. Net force is always the same direction as acceleration, so that means acceleration is that way. Acceleration for this one is forward. There is no acceleration for this one because there's no net force, and your acceleration is in this direction because it's backwards. When we talked about equilibrium, we know that that meant that the net force ended up equaling 0. And if you are at 0, that means that there is no acceleration. Why? Because of Newton's second law. We know that the net force is equal to mass times acceleration. So if this is 0, then F net has to be 0. Important to remember. Now, if there is no acceleration, that either means that an object is not moving, or in order to have no acceleration, you can also be at constant velocity. So keep that in mind. If acceleration equals 0, then you're either not moving or at constant velocity. Let's take a look at this picture again of the girl on the bicycle. This time, friction is 15 newtons backwards and driving force is 15 newtons forwards. So the forward and backward forces cancel out. So net force equals 0. Also, the up and down forces of the ground pushing up on her and also her weight pushing down balance out. So in the y-axis, the net force equals 0 as well. That means that this bicycle is not accelerating. But does that mean that the bicyclist is not moving? No, not necessarily. If the bike was already moving and then the forces are canceled out, that just means she's moving at a constant velocity and not accelerating. But simply by pedaling, she's just overcoming friction so that she can stay at a constant velocity. Some people still might question, well, how is that possible? How can you have no overall net force and still be moving? Don't forget about inertia. An object in motion stays in motion. So as soon as she was moving and she canceled out those forces, the object wants to continue moving, and that's why you can have constant velocity. If we take a look at a physics book on a table over here, the book pushes down with its weight, and the table pushes up with something we like to call support force or normal force. Let me clear out some of these drawings here. That support force or normal force is just what balances the weight of an object. So since the physics book has weight pushing down, the table pushes up with the same amount. And we call that again the normal force or support force. The same is true with the bicycle. If her weight is 700 newtons, the ground pushes up by 700 newtons as well. That upward force is called the support or the normal force. There are plenty of examples to go over with Newton's second law. For example, if we're looking for acceleration in this one, and that will result with a 12 Newton net force, this would be our F net, and it's applied to a 3 kilogram object, we can simply use our equation F net equals ma. Now it also asks you about a 6 kilogram object as well. If that's the case, we know that the acceleration will be greater for the less massive object. Why? Because its inertia will be less. So if they're both exerting with the same force, but one object is lighter than the other, the lighter object will accelerate more. Remember the golf ball and the truck being hit by the golf club? The same idea applies here. So I encourage you to try some of these problems out, and we also have practice problems on a worksheet as well for you to consider. But if you need any extra help, come on in and see me, and we can definitely talk about it. But this is going to conclude our idea of Newton's second law. Best of luck, and thanks again for listening.